So let's continue in chapter 14 and do acid-base titrations. Now, what is a titration? It is simply an accurate way to figure out how much acid or base we might have in a sample. We've done this in lab. How you might do this in lab, if you're going to monitor the pH, is you would have a nice burette. And in your burette, you're going to put in a acid or base that you know the concentration of. In here, you're going to have the sample. The sample is called the analyte. The stuff in the burette is called the titrant. And what we're going to do is we're going to add the stuff in the burette carefully while monitoring the pH to figure out what or how much acid or base we have in our sample. We do this in lab. We're going to do it on a little plate that will stir for us, and we're going to keep track of the pH using a pH meter. We can also take and we can add an indicator and figure out when the pH is going to change. When we have done this and we have the number of moles of the acid in our sample are equal to the number of moles of base that we have added, we are at the equivalence point. This is where the moles of the two are equal. For the case of a strong acid, strong base titration, we're going to find out that at the equivalence point, the pH is going to be 7, and we're going to plot our data. So the only way to do this is really to just do this. So with this in mind, if we have 50 mils of HCl titrated, and it's 0.1 molar, with 0.1 molar NaOH, and notice that these values are the same in terms of concentration. That is on purpose. Our job is not to do complicated math. It really is to try to understand the changes in the pH. So we're going to do 3 parts of this. We're going to do the pH initially with no base added, pH halfway to the equivalence point, 25 mils of base added, and pH at the equivalence point, 50 mils of base added. As we do this, we have to keep track of the volume total because we're going to need the volume total as we go. Here with no base added, it's not a problem. We haven't done a dilution. Halfway to the equivalence point, we had 50 mils. We added 25 mils for a total volume on this one of 75 mils. Here our total volume at the end is 50 plus 50, and we have a total volume of 100 mils. Do pH initially. Initially, what we're doing is we're measuring the pH of the HCl. We have 0.1 molar. This is a strong acid. We're going to stop and identify it every time. We know because it's a strong acid that the concentration of the H3O plus is going to be the same as the initial concentration for acid, because our acid is 100% dissociated, and so the concentration is 0.1, and our pH is a minus base 10 log 0.1, and our pH of this solution 1. Again, we can only do that because HCl is a strong acid. All right, so second part of this right here, we're going to do halfway to the equivalence point. Halfway to the equivalence point is where it's halfway to be neutralized, and neutralized would be where we'd add 50 mils of sodium hydroxide. This is a nice strong acid and a strong base, so we know what we have here in our solution is H plus and Cl minus. We're going to ignore the Cl, it's inert. We're adding sodium hydroxide, which is Na plus and OH minus, and ignoring the Na plus. Now, when we have strongs, we know we need a mole chart. And we remember that moles here are equal to volume in liters multiplied by molarity. So our mole chart will be H plus plus OH minus is going to go into H2O. We're going to have ICF, initial, change, and final. We're going to use that when we have moles. So the initial amount of the H plus will be 0.050 liters multiplied by 0.1 molar, and that's going to be 0.005 moles. The hydroxide is 0.025 liters. Remember, 25 mils divided by 1,000 to get our volume in liters. Our molarity is 0.1, so 0.0025. We're going to ignore the water. The smaller value is our limiting reagent, so we're going to subtract 0.0025. There's nothing to add on the product side because this is weak and there are no products that we care about. We're just making water, giving us 0.0025 and 0. So we have 0.0025 moles of H plus. We've got to remember to stop and analyze always when we get to our final point. This is a strong acid. We know that pH is equal to the minus base 10 log of concentration of the H plus, which means we need moles per liter. So that's going to equal minus 0.0025 moles going to equal 0.0025 moles for the concentration divided by the volume. Now, the volume is going to be 50 plus 25 or 75 mils will be equal to my volume total, or 0.075 liters, again, divided by 1,000. So the pH is going to be minus base 10 log of the moles, 0.0025, divided by the volume, because again, I have to have molarity, which is 0.075 liters. And our pH for this solution is going to be 1.48. So halfway to the equivalence point, my pH has gone from 1 to 1.48. So what about at the equivalence point? Well, at the equivalence point, our reaction is the same. H plus OH minus is going to go into H2O. This is still strong. We still need a mole chart. So we're going to do ICF. But now we're going to realize that our volumes and our molarities are the same, or at the equivalence point, inherently, we know the moles of this are equal to the moles of this. So what we have, 0.050 liters times 0.1, and this is 0.050 liters multiplied by 0.1 molar. We're going to ignore the H2O. This is 0.005, 0.005. And all of it is going to react. We are at the equivalence point, which means by definition, the moles of the added base will equal the original moles of acid in the sample. So what does this tell us? This tells us that we have no H plus, we have no OH minus, no extra either, we have just water. And we say, okay, we can do this. If we have just water, our pH is 7. And anytime that we have a strong titration at the equivalence point, we're going to shorthand with that is that in EQPT, our pH will be 7. So what does this graph look like? We're going to start out with a very acidic solution. Our pH is going to rise very slowly. Again, this is a log function, so it doesn't go up as fast as you might think. It's going to go up very, very abruptly when we get near the equivalence point, because this is a strong at the equivalence point. Our pH will be 7. And after the equivalence point, if you want to do the math, you can realize that you're going to have hydroxide in excess. And you can figure out the pH by figuring out how much hydroxide is in that solution.